The universe has 10 scientifically proven ways to die, and some of them are so disturbing they'll rewrite your understanding of reality itself, from a slow fade into frozen nothingness that takes longer than you can imagine, to an instant rewrite of physics that happens at light speed with zero warning, to a scenario so dark it suggests you might not even be real right now. Today, I'm breaking down every way the universe could actually end, ranked from the most predictable to the most reality-shattering. And trust me, the last one will mess with your head. Heat death. The universe doesn't go out with a bang. It goes out with the slowest, coldest whimper imaginable. Here's the thing, the second law of thermodynamics has never been wrong. Ever. Entropy always increases, energy always spreads out, and given enough time, the entire universe reaches thermal equilibrium. No more stars, no more galaxies, no more anything happening anywhere. Just an endless ocean of particles at near absolute zero, drifting through eternal darkness. The timeline is absurd. Star formation ends in about 100 trillion years. The last stars burn out after 10 trillion years. By then, every galaxy except our local group has been pushed beyond the cosmic horizon by accelerating expansion. Future astronomers would see an empty sky and have zero evidence the rest of the universe exists. After the stars die, the cosmos becomes an ocean of dead stellar remnants. White dwarfs, neutron stars, black holes, all floating in absolute darkness. And that's just the beginning. Eventually, even those remnants are destroyed by proton decay and Hawking radiation. What's left is a bath of photons and particles at 10 to the negative 30th Kelvin. That's the de Sitter temperature, calculated as the Planck constant times the Hubble parameter divided by 2 pi. The universe doesn't freeze exactly, it just forgets how to do anything interesting. The physics is bulletproof. Rudolf Clausius figured this out in 1865. The entropy of the universe tends to a maximum. The 1998 discovery that expansion is accelerating sealed the deal. Dark energy pushes galaxies apart forever. No gravitational collapse, no energy concentration, just an endless frozen equilibrium. Fred Adams and Gregory Laughlin mapped out the full timeline in the 5 ages of the universe. They call the endpoint the dark era. A photon drifts past once every trillion years. Its wavelength is stretched larger than today's entire observable universe. This is eternity, not destruction, but the quiet victory of the most fundamental law in physics. But at least heat death takes 10 to the 100th years to finish the job, unlike what comes next. Big Crunch. The Big Bang played in reverse is exactly what it sounds like. Everything collapses back into a singularity. For decades, this was considered dead. The 1998 discovery of accelerating expansion killed it. If dark energy is pushing galaxies apart faster and faster, gravitational collapse seemed impossible. Case closed. But then DESI dropped a bomb in 2024 and 2025. The Dark Energy Spectroscopic Instrument analyzed nearly 15 million galaxies and found something nobody expected. Dark energy appears to be weakening over time, not staying constant, weakening. And if dark energy can change, it can turn negative, which means expansion can reverse. Cornell physicist Henry Tide published a model in September 2025 that puts the universe's total lifespan at just 33.3 billion years. We're already 13.8 billion years in. His model predicts expansion continues for about 11 billion more years. Then an 8 billion year contraction phase ends in a crunch. His calculations use an action-like field with a negative underlying cosmological constant. What you'd experience has been described by Harvard astrophysicist Avi Loeb. The night sky gradually brightens as galaxies converge. The cosmic microwave background shifts from invisible microwaves to infrared, then visible light. The entire sky glows. Around room temperature, there's a brief habitable cosmic epoch lasting about 7 million years. Then temperatures exceed the sun's surface at 5,800 Kelvin. Stars literally boil away because they can't radiate heat anymore. In the final minutes, atomic nuclei shatter into quark gluon plasma. Space itself becomes a fireball of near infinite temperature. Then neither time nor space remains. The Big Bang, but backwards. The current consensus is this remains unlikely, but DESI's results showing 2.8 to 4.2 sigma evidence for evolving dark energy have revived serious discussion. Upcoming data from Euclid in October 2026 and the Roman Space Telescope launching May 2027 will be decisive. At least the Big Crunch is a clean ending, unlike the possibility that the universe just keeps rebooting itself forever. Big Bounce. What if the universe never actually ends? What if it just restarts? The Big Crunch collapses everything into a singularity and game over, right? But quantum mechanics says no. At extreme densities near the Planck scale, quantum gravitational effects create a repulsive force that halts the collapse and triggers re-expansion. The universe breathes, expanding, contracting, bouncing, over and over, potentially forever. The physics comes from loop quantum cosmology, founded by Martin Borgewald at Penn State in 1999. The core idea is that spacetime isn't smooth at the smallest scales. It's granular, made of discrete atoms of space at about 10 to the negative 35 meters. The modified Friedmann equation contains a factor that prevents infinite density. When density approaches about 2.1 times 10 to the 96th kilograms per cubic meter, the expansion rate goes to zero and reverses. No singularity, just a bounce. Three major variants exist. The Steinhart-Turok cyclic model uses string theory's extra dimensions. Our universe is a three-dimensional brane that periodically collides with a parallel brane. Each collision looks like a Big Bang. Roger Penrose's conformal cyclic cosmology takes a different approach. The infinitely expanded, infinitely cold far future of one aeon is mathematically identical to the hot, dense Big Bang of the next. Penrose claims he found evidence in 2020, Hawking points. Anomalous hotspots about 4 degrees across in cosmic microwave background data at 99.98% confidence. But a 2022 machine learning analysis found these consistent with noise. The bounce itself happens in 1 Planck time. That's 10 to the negative 43 seconds. Temperature hits 1.4 times 10 to the 32nd Kelvin. Nothing survives except the universe itself. But here's where it gets weird. Martin Borgewald noted something he calls cosmic forgetfulness. Quantum uncertainty during the bounce erases most information about the previous universe. Each cycle is born amnesiac. The universe restarts but has no memory of what came before. A 2022 paper by Marcin Kisielewski published the first full-loop quantum gravity calculation showing periodic evolution. Big bounce to expansion to big crunch to big bounce, cyclically. But at least a bouncing universe preserves existence itself, unlike what happens when the building blocks of all matter just dissolve. Proton decay. The proton is supposed to be eternal, the fundamental building block of all atomic matter, stable forever, except it's not. Grand unified theories predict that quarks inside protons can spontaneously transform into leptons. The proton decays into a positron and a neutral pion. The pion immediately decays into 2 gamma rays. The positron annihilates with an electron, producing more photons. Net result, all matter converts to radiation. Every atom in every planet, star, and living thing eventually dissolves into flashes of light. The estimated half-life is somewhere between 10 to the 34th and 10 to the 41st years, depending on which grand unified theory is correct. The original Georgy Glashow model from 1974 predicted 10 to the 31st years and has been ruled out by experiment. Supersymmetric models predict 10 to the 34th to 10 to the 36th years. Right now, physicists in Japan are watching 50,000 tons of ultra-pure water, waiting for a single proton to wink out of existence. Super Kamiokande is a cathedral-sized detector 1,000 meters underground in the Kamioka mine. It's been searching since 1996. Its 11,000 photomultiplier tubes watch for the faint Cherenkov radiation produced by decay products. After 450 kiloton years of exposure, the result is 0 confirmed detections. The current lower limit on the proton lifetime is 2.4 times 10 to the 34th years at 90% confidence. But the next generation experiment changes everything. Hyper Kamiokande is 8 times larger than Super Ki with 258,000 tons of water. Cavern excavation completed in June 2025 and operations begin in 2027 or 2028. After 20 years, it will push sensitivity to 10 to the 35th years, probing the prediction range of several still viable models. What the death of matter looks like is pathetic. By 10 to the 36th years, effectively all free protons have decayed. White dwarfs powered by the trickle of energy from proton decay glow at about 400 watts, 4 light bulbs. An entire galaxy of such objects would be dimmer than a single normal star today. Neutron stars disintegrate, planets crumble. All solid matter gradually transmutes into radiation and leptons. Matter itself has an expiration date. Chemistry, structure, everything material is temporary. The universe spent 13.8 billion years building atoms and will spend 10 to the 34th years tearing them apart. But at least protons take unimaginable time to decay, unlike the black holes that become the universe's last organized structures before they vanish too. Black hole. Evaporation. After proton decay eliminates all matter, only black holes remain. They are the universe's last repositories of concentrated energy. its final lighthouses in an ocean of darkness, and even they are doomed. Stephen Hawking's 1974 Nature paper revealed the mechanism. Virtual particle-antiparticle pairs constantly form near the event horizon. Occasionally one particle falls in while the other escapes, carrying away energy. The black hole slowly bleeds mass. And here's the twist. The black hole's temperature is inversely proportional to its mass. A solar mass black hole has a temperature of just 60 nanokelvin, far colder than the cosmic microwave background's 2.7 Kelvin. This means all astrophysical black holes currently absorb more energy than they emit. Net evaporation won't begin until the CMB cools below their Hawking temperature, trillions of years from now. The evaporation timeline spans breathtaking scales. A stellar mass black hole at 10 solar masses evaporates in about 10 to 70 years. Sagittarius A star, the Milky Way's central black hole at 4 million solar masses, lasts about 10 to 87 years. The largest supermassive black holes at around 10 to the 11th solar masses endure for roughly 2 times 10 to the 100th years. That's a 1 followed by 100 zeros. Truly monstrous black holes formed from supercluster collapse could persist to 10 to the 106th years. But here's where it gets dramatic, and the final moments are spectacular. As a black hole loses mass, its temperature rises and radiation intensifies, a runaway process. In the last 0.1 seconds, a black hole releases at least 10 to the 30th ergs in a brilliant flash of gamma rays and particles. It briefly illuminates the cosmic darkness like a firecracker in an infinite void. Then it winks out of existence. The black hole information paradox drove theoretical physics for 50 years. Hawking's original calculation implied information falling into black holes is permanently destroyed, violating quantum mechanics. But a major breakthrough came in 2019 and 2020 when Amhiri, Engelhardt, Maroff, and Pennington used gravitational island calculations to derive the Page curve. Information is preserved. The precise mechanism remains debated, but most physicists now believe information survives evaporation. A number like 10 to the 100th years breaks human cognition. The current age of the universe at 13.8 billion years is essentially zero by comparison. The image of a lone black hole radiating imperceptibly in an otherwise dead universe for Google years before its final flash is hauntingly dramatic. After that flash, the last event in the universe, nothing interesting ever happens again. But at least black holes take forever to evaporate, unlike the quantum tunneling endgame that turns everything into iron stars. This scenario only applies if protons are stable. If they decay first, this is preempted. But given truly infinite time, quantum tunneling converts all ordinary matter into iron-56, the nucleus with the lowest mass per nucleon and therefore the most thermodynamically stable element in the universe. Lighter elements slowly fuse into iron via picnonuclear fusion. That's cold quantum tunneling through Coulomb barriers at near absolute zero temperatures. Heavier elements undergo fission or alpha decay toward iron. Stellar remnants become cold, dark spheres of pure iron stars. The timescales are incomprehensible even by cosmological standards. Freeman Dyson calculated in his 1979 paper, Time Without End, that the conversion takes approximately 10 to the 1,500th years. For comparison, the number 10 to the 1,500th is so large that writing it out would require more digits than there are particles in the observable universe, only about 10 to the 80. Matt Kaplan from Illinois State University calculated in a 2020 paper that some white dwarfs could undergo black dwarf supernovae. Iron core collapse triggering type 1, A-like explosions at around 10 to the 1,000th years. These would be the universe's last stellar explosions. Detonations in a cosmos that has been dark for over 1,000 orders of magnitude of years. Even iron stars don't last forever. On timescales of 10 to the 10th to the 26th years to 10 to the 10th to the 76th years, quantum tunneling rearranges iron stars into neutron stars, which then quantum tunnel into black holes, which then evaporate via Hawking radiation. The mathematical notation itself breaks down trying to express these numbers. They are double or triple exponentials. The timescales involved are so extreme they cease to have any meaningful relationship to human experience. The number 10 to the 1,500th cannot be visualized or contextualized. It exists purely as abstraction. The idea that quantum mechanics, given enough time, transmutes every atom in the universe into iron, turning stars into cold dark monuments to entropy, is both scientifically rigorous and deeply eerie. But at least iron stars take numbers that break notation to form, unlike the Big Rip, which has an actual countdown clock. Big Rip. Dark energy doesn't just accelerate the universe's expansion, it accelerates the acceleration. And if dark energy's equation of state parameter W is less than -1, called phantom energy, the energy density of empty space increases as the universe expands. This creates a runaway feedback loop. More expansion creates more dark energy, creates faster expansion. The Hubble parameter diverges to infinity in finite time, and everything in the universe from the largest structures to individual atoms is progressively ripped apart. Robert Caldwell from Dartmouth College coined phantom energy in 1999 and co-authored the definitive Big Rip paper in 2003 with Mark Kamiankowski and Nevin Weinberg. Their illustrative timeline using W equals -1.5 places the Big Rip about 22 billion years from now and unfolds as a precise countdown. T minus 200 million years. Galaxy clusters unbind. Gravitational bonds between clusters are overwhelmed. T minus 60 million years. Individual galaxies disintegrate. Stars drift apart from the Milky Way. T minus 3 months. The solar system unbinds. Planets fly away from the sun. T minus 30 minutes. Stars and planets are torn apart by tidal forces. T minus 10 to the -19 seconds. Atoms are destroyed. Electrons stripped. Nucleus shattered. T equals 0. The scale factor reaches infinity. Space-time itself is torn apart. The critical physics hinges on W. For a cosmological constant, W equals -1 exactly. Dark energy density stays constant and no rip occurs. For W less than -1, energy density scales as the inverse cube of 1 plus W power of the scale factor. And since -3 times 1 plus W is positive when W is less than -1, density grows with expansion. This violates the null energy condition, a fundamental assumption in general relativity. Current measurements put W tantalizingly close to -1. Planck 2018 data shows W equals -1.02, 8 plus or minus 0.031. The Chandra X-ray Observatory constrains W between -0.907 and -1.075. DCI's 2025 results suggest W has actually crossed the phantom divide over cosmic time, transitioning from phantom-like in the past to quintessence-like today around redshift z equals 0.5, about 5 billion years ago. This inverse phantom crossing actually trends away from a future Big Rip, but doesn't rule it out if dark energy's behavior changes again. What you'd experience is a countdown. Billions of years out, the night sky empties as galaxies vanish beyond a shrinking cosmic event horizon. Months before the end, the sun loses its planets. Minutes before, the Earth itself flies apart. In the final fraction of a second, your atoms disintegrate. As PBS Nova described it, about 30 minutes later, all atoms will burst like fireworks. Then, in a mere fraction of a second, space itself will tear to shreds. Unlike heat death's trillion-year fade, this is a specific moment of total annihilation. The progressive scale of destruction creates a narrative escalation. Superclusters, then galaxies, then stars, then atoms. The destruction isn't just of matter, but of space-time itself. But at least the Big Rip gives you billions of years of warning, unlike the disturbing discovery happening right now. Dark energy evolution. This isn't a single-end scenario. It's the disturbing discovery that the force controlling the universe's fate appears to be changing in real time, and we don't know where it's headed. DZ's 2024 and 2025 results represent the most significant challenge to standard cosmology since the 1998 discovery of cosmic acceleration. If confirmed, dark energy isn't a fixed cosmological constant. It's a dynamic, evolving entity whose behavior could lead to any number of endpoints, some not yet imagined. The DESI bombshell landed in 2 waves. In April 2024, the Dark Energy Spectroscopic Instrument released its first-year analysis of 6 million galaxy redshifts, showing hints that dark energy's equation of state parameter W varies with time. In March 2025, DESI's second data release, based on nearly 15 million galaxies and quasars, strengthened the evidence to 2.8 to 4.2 sigma, depending on which external datasets are combined. The 5 sigma discovery threshold hasn't been crossed but as DESI co-spokesperson Will Percival stated, it's looking more and more like we may need to modify our standard model of cosmology. The parameterization used is W of A equals W0, plus WA times 1 minus A, where A is the scale factor and W0 and WA describe dark energy's current value and rate of change. The DESI data suggests dark energy was phantom-like, Duabios less than -1 in the past and has crossed to quintessence-like, W greater than -1 today, with the transition occurring around 5 billion years ago. This phantom divide crossing is theoretically significant because a single canonical scalar field cannot cross W equals -1. It requires either multiple fields, modified gravity, or entirely new physics. The implications for the universe's fate are profound and uncertain. If dark energy continues weakening, expansion could eventually slow and reverse, reviving the Big Crunch. If it stabilizes, we get a modified heat death. If it strengthens again, the Big Rip returns. If it behaves in ways not captured by simple parameterizations, we're in genuinely uncharted territory. This intersects with other cosmic puzzles. The Hubble tension, the 5 sigma discrepancy between local measurements of the expansion rate at about 73 kilometers per second per megaparsec and early universe measurements at about 67.4 from Planck CMB data remains unresolved. DESY's results actually increase rather than alleviate this tension. JWST has discovered impossibly early massive galaxies at redshift Z equals 7 to 9 that strain standard model predictions. Mustafa Ishaq-Burshaki from UT Dallas, DESI Cosmological Interpretation Co-Chair, stated with a 4.2 sigma significance, "I think we are getting to the point of no return." Durham University's Carlos Frank warned that if confirmed, our earlier understanding goes out the window and essentially we have to start from scratch. Unlike theoretical scenarios that might happen in 10 to the 100th years, this is happening now. The force governing the universe's destiny is behaving unpredictably, and the next few years of data from Euclid cosmology results in October 2026, continued DESY releases, and Roman Space Telescope launch in 2027 may fundamentally rewrite our understanding of the cosmos's future. The scariest thing about an evolving dark energy isn't any specific outcome. It's that we genuinely don't know where it's headed. But at least dark energy changes over billions of years, unlike false vacuum decay, which could erase reality at the speed of light. False vacuum decay. The quantum fields underlying all of physics may not be in their lowest energy state. Our universe may be sitting in a false vacuum, a local energy minimum, like a ball resting in a shallow depression halfway up a hill with a deeper valley below. Through quantum tunneling, a tiny region of space could spontaneously drop to the true vacuum state, nucleating an expanding bubble of completely different physics. This bubble expands at the speed of light. Inside it, particle masses, force strengths, and fundamental constants are all different. Atoms cannot form. Chemistry is impossible. Everything the bubble touches is instantaneously and totally annihilated. You would never see it coming. The physics centers on the Higgs field. The brute angular Higgs field permeates the universe with a vacuum expectation value of about 246 giga-electronvolts. Quantum corrections, primarily from the top quark's large Yukawa coupling, modify the Higgs potential at high energies. The Higgs self-coupling lambda runs negative at around 10 to the 10th to 10 to the 12th giga-electronvolts, causing the potential to develop a second deeper minimum near the Planck scale. This makes our electroweak vacuum potentially metastable. The key number is the Higgs boson mass, 125.25, plus or minus 0.17 giga-electronvolts, discovered at CERN on July 4, 2012. The critical mass for absolute stability is about 126 giga-electronvolts. Our measured value falls just below this threshold. The landmark 2012 analysis by Degrassi and colleagues found absolute stability excluded at 98% confidence for masses below 126 giga-electronvolts. Butazzo and colleagues in 2013 showed the measured values sit strikingly close to the stability-metastability boundary, a mysterious near-criticality. Benyakov and colleagues in 2015 confirmed metastability, but showed stability is possible if true parameters are only 1.3 standard deviations from current best estimates. Sidney Coleman from Harvard developed a theoretical framework in his 1977 paper, Fate of the False Vacuum, Semi-Classical Theory. With Frank DeLucia in 1980, he extended it to include gravity, finding that gravitational effects generally suppress decay, but that the interior geometry of the bubble would be anti-de Sitter space, likely collapsing into a singularity almost immediately. Their famous quote, "Vacuum decay is the ultimate ecological catastrophe." The estimated vacuum lifetime within the standard model is about 10 to the 300th years, with a 95% confidence interval spanning 10 to the 65th to 10 to the 725th years due to top quark mass uncertainties. But catalysts could dramatically accelerate the process. A 2014 to 2016 series of papers by Ruth Gregory and colleagues showed black holes could seed bubble nucleation, though a 2019 finding revealed that rapidly spinning black holes actually stabilize the false vacuum. What you'd experience is nothing, then nothing different, then nothing at all. The bubble wall approaches at light speed. No signal can outrun it, so there is zero warning. At the boundary, the Higgs field value changes discontinuously. Electron masses shift. The electromagnetic and weak forces potentially remerge. Nuclear binding energies change. Atoms dissolve. Chemistry ends. The destruction isn't just physical. The laws of physics themselves are rewritten. As cosmologist Joseph Licken from Fermilab put it, the universe is like a house of cards, and the big slurp is the gust of wind that could bring it all down. One crucial caveat. Due to accelerating expansion, a vacuum decay bubble cannot consume the entire universe. Galaxies beyond about 13 billion light years recede faster than light. The bubble would devour a large but finite region, leaving the rest intact, at least until more bubbles nucleate elsewhere. False vacuum decay is the only scenario that could happen right now with zero warning, destroying not just matter, but the fabric of physical law. It doesn't end the universe with heat or gravity or expansion. It replaces it with an alien reality where none of our physics applies. The measured Higgs mass sits tantalizingly close to the instability boundary, and no conceivable technology could detect it, prevent it, or survive it. But at least false vacuum decay only destroys physics, unlike the final scenario which proves nothing you know is real. Boltzmann brains. This is not a physical destruction of the universe, it's something worse. It's a proof that in certain cosmological models, your existence is almost certainly a momentary hallucination. In an eternal, thermodynamically dead universe, random thermal fluctuations will eventually produce any configuration of matter, including a functioning human brain complete with false memories of a life, a planet, and a universe that never existed. Given infinite time, such random Boltzmann brains arise with probability 1. And because a solitary brain, a low complexity fluctuation, is exponentially more probable than an entire universe, a high complexity fluctuation, the overwhelming majority of observers in an eternal cosmos would be Boltzmann brains, not evolved beings in a real universe. The logic is devastatingly simple. Ludwig Boltzmann himself first raised a version of this argument in 1896. Arthur Eddington articulated the paradox more clearly in 1931. Andreas Albrecht and Lorenzo Sorbo coined the term Boltzmann brain in 2004. The argument runs if the universe persists in thermal equilibrium forever as predicted by heat death with a positive cosmological constant, then over timescales of about 10 to the 10th to the 66th years or more, random fluctuations will spontaneously assemble conscious observers with fabricated memories. Statistically, you are overwhelmingly more likely to be such a phantom than a real observer who evolved in a structured universe. Your memories of the sun, earth, and your entire life would be false. Brief electrochemical accidents in the void. This isn't just philosophical navel-gazing, it's a serious constraint on cosmological theories. Sean Carroll from Caltech and Johns Hopkins has argued that any viable theory of the universe must predict that we are not Boltzmann brains. If it doesn't, the theory is self-undermining. Alan Guth from MIT, father of inflationary cosmology, has worked extensively on this problem. Brian Greene acknowledged Maynard's, "I am confident that I am not a Boltzmann brain. However, we want our theories to similarly concur, but so far it has proved surprisingly difficult." Carroll proposed a striking resolution connecting this to false vacuum decay. If our vacuum is metastable, it will decay before Boltzmann brains have time to form. Vacuum decay becomes, in Carroll's words, a feature, not a bug. The universe destroys itself to preserve the coherence of observation. Carroll and Jennifer Body showed this works if the vacuum decay timescale is much shorter than the Boltzmann brain formation timescale of about 10 to the 10th to the 66th years, which the standard model estimate of about 10 to the 300th years satisfies. A 2025 paper by Mozersky in the journal Philosophies offered new mathematical analysis of the Boltzmann brain problem in infinite time scenarios, arguing that standard probability measures break down in eternal universes and that the paradox may reflect the inadequacy of our mathematical tools rather than a genuine metaphysical crisis. Boltzmann brains don't merely destroy the universe, they undermine the concept of reality itself. Every other scenario on this list assumes that our observations are real, that the universe exists as we perceive it, and that physical theories describe actual events. The Boltzmann brain paradox challenges all of these assumptions simultaneously. It's the ultimate cosmic horror. Not that the universe will end, but that it may never have been real in the first place. It is, as Carroll calls it, cognitively unstable. A conclusion that, if accepted, invalidates the very reasoning used to reach it. If you enjoyed this video and want to see more, click the video on the screen now.